Okay, good evening. So I thought we would talk a little bit about center of mass, since that's what we're going to be doing next, and that'll lead us into talking about momentum and collisions and impulse and all these type things. So the idea of the center of mass of an object, and I'm talking about a rigid object, a steel plate, a ball, could be an irregular object of some kind. This idea of center of mass is, it's the point at which if you hold the object, it's as if all its mass is concentrated at that point. It's the balance point, okay? So if I take an object like this spoon, since I'm here in my little made-up studio, and I can balance it maybe. Okay, yep, that's pretty close. That's not bad. Okay. Something like that. Okay. So somewhere along here, along this axis, would be the center of mass of this object along this axis. It also has a center of mass along this axis. It also has a center of mass along this axis. So depending on the shape of the object and how it's oriented, that's what gives you that balance point. It's that point at which all the mass is concentrated, as if all the mass is concentrated. So we're going to look at some ways to calculate center of mass for point particles, and then we'll also look at some ways to calculate center of mass for irregular objects. When I say irregular, I mean a little bit irregular, okay? So let's take an example like here's the x-axis, and here's 0, and here's some point particle, and out here is another point particle, okay? Let's say that this has a mass of, this is M1, and it equals 5 grams. This is M2, and it equals 10 grams. Okay? So we've got a 5-gram object over here, a 10-gram object over here, and it's not symmetric about the axis. Let's say that this distance is negative, or this position rather is negative, let's make this negative 3 centimeters, and this position is over here at positive 5 centimeters. Okay? So we've got two objects on the x-axis, a 5-gram object, a 10-gram object, and we want to find where this center of mass. So you can imagine it's like a little dumbbell, and it's not equally weighted. This has twice the mass of this one, and we want to find where that balance point is. What you do is you take a weighted average. So the x center of mass, I'm just going to call it xcm, is equal to 1 over the total mass times the sum over I of m sub I x sub I. Okay? So what you do is you take the mass, M1, its position. You add it to M2, its position. And you do have to pay attention to the negatives. This is not just a magnitude of how far it is from the origin. Okay? And then you divide by the total mass of the system, all right, which in this case is just M1 plus M2. Now let's think about units. This has units, if we keep it in grams and centimeters, this has units of grams, centimeters. We're going to divide out grams, and that's going to give us an x center of mass in centimeters, okay? So let us do that now. I want to calculate the center of mass. Can you kind of figure out where this center of mass is going to be anyway? I mean, it's going to be Oh, let's see, we got 10 grams over here and 5 grams over here, so, you know, somewhere in here, right? It's like the spoon. It's much heavier on this side than it is this side, and you get a center of mass over in here somewhere. So I would expect the center of mass to be somewhere in the positive range, okay? So let's see. For X center of mass, that's going to be, I'm going to write out this summation. That's going to be M1X1, which is 5 grams times -3 centimeters. That's the position, plus 10 grams and the position of M2, which is 5 centimeters, and divide that by the total mass. The total mass is 15 grams. Okay? So we'll do this calculation. This is equal to -15 gram centimeters. I don't know, gram times centimeters. Plus 50 gram centimeters divided by 15 grams. Okay, so 50 minus 15, I think that's 35. So this is equal to 35 gram centimeters divided by 15 grams. Okay, and that's equal to what? Well, 35 over 15, let's see, that's 6 over 3. No, that's not right. What is that? That's 7. 7 over 3. So it's 7 over 3. I don't know if you guys can see this. I hope you can. So this is equal to 7 over 3 centimeters. Okay. So that's 2.3333, somewhere around here. Okay. And that's what we expected, right? 7, is that right? 35 over 15. Yeah, okay. 2 1/3. Is that right? Yeah. Where's my calculator? Yeah, I left my calculator in the house. I can't do these in my head without you guys here to help me. I don't have any confidence. Yeah, that's right. Okay. Okay. Anyway, this is the idea. You sum up the mass times its position, take the sum, and divide by the total mass, and that gives you the center of mass. This is one dimension. Let's do a two-dimensional problem. Okay. So let me just say in several dimensions, if we have more than one dimension, for X center of mass, that's equal to 1 over M times the sum over I of M sub I, X sub I. Y center of mass, well, it's the same thing. It's 1 over the total mass times the sum over I of M sub I, Y sub I. Okay, so you do the same thing in the Y direction, and Z center of mass, you probably guessed it, it's 1 over M times the sum over I of M sub I, z sub I. Okay? So orient an object along some XYZ coordinate system. You can calculate the center of mass along each direction. Okay? And we're going to generalize this shortly to continuous objects, things like spheres and plates and so forth. Okay? So let's look at an example of an object. I'm still going to use point particles, but I'm going to make this 3D. So let's say you have, it doesn't matter what we call it. This is M1, and it's at point, let me give it a mass. Okay. M1 is equal to 7 grams, and it's at the point 4 centimeters. 4 centimeters. Okay? That's M1. That's the X coordinate. That's the Y coordinate. Here's M2. M2 is equal to 5 grams, and it's at 4 centimeters, 0 centimeters. Okay? And let's put one over here. I'll put it, maybe about right here. And this is M3, and it's equal to 15 grams. And it is at -2 centimeters, 0 centimeters. Okay? So what we can do here, we can calculate the center of mass in the X direction. So where would the balance point be along this direction? And then where would the balance point be along this direction? Okay? So let's do the X direction first. So X center of mass is equal to 1 over the total mass. Well, the total mass is 12 plus 15. I didn't make it too easy on myself. 12 plus 15 is 27 grams. Okay? And then we have to sum up the positions times the little masses. All right? So we have M1. M1 is 7 grams at 4 centimeters. I'm only looking at the X direction. Plus M2 is 5 grams at 4 centimeters. Plus M3 is 15 grams at -2 centimeters. -2 centimeters. Okay? Do the calculation. Well, let's see, what do we got? 1 over 27 grams, and this is 28 plus 20 plus a -30. Okay? So I think that comes out to be 18. This is in gram centimeters. Okay? That's 48 minus 30, that's 18. So this is equal to 18 over 27 centimeters. So that's the X position of the center of mass along here, okay, or along the X direction. Okay? Let's look at the Y direction. Unfortunately, I don't have a lot of board space, so we'll have to erase it, but fortunately this is on video, so you can run it back and watch it again. If I've made some mistakes, which I'm sure I have, let me know. All right. For the y direction, so y center of mass, I do the same exact thing except now I'm moving along the y direction. So I have 1 over 27 grams. Then I'm going to look at each of the masses and their positions. M1, 7 grams, y position, 4 centimeters. Plus M2, 5 grams. Position, 0 centimeters. M3, 15 grams. Position, 0 centimeters. Well, this is pretty simple in the y direction because all I have is 28 over 27. So this is equal to 28, 4 times 7, divided by 27, and that is centimeters. Okay? Does that make sense? Well, let's see. You've got a total of 20 grams down here and 7 up there. So it's saying in the y direction that center of mass is somewhere here. Okay? Yeah, it's heavier down here. You don't have as far a distance down here for the balance point. Remember the stuff that we did way back when in lab with torque and balancing those little masses, then you can sort of, if you think back on that, you can get a feel for the position of the center of mass in the y direction. This is a 2D model. These are point masses, so we don't have any center of mass in the z direction, except if there were a z direction, it would be at z equals 0 because all the z coordinates are 0. This is a 2D layout. Okay? All right. We can generalize this. We can generalize this to objects that are not point masses. And what we do is we turn that summation into an integral. Okay? So you get the x center of mass is equal to 1 over the total mass, which, you know, depending on how the object looks and where, you know, the shape of it, the density of it, and so forth. I'll talk a little more about this in a second. You may have to do some calculation based on the geometry of the object to get this total mass. Okay? Then you're going to integrate over the x direction times dm. This is some little bit of mass. You can think of it as delta m, okay? And this is, we break it up into little bits of mass. So you're summing over this is the position, and these are those little point masses, okay? Same thing, you know, generalize this to y center mass. It's the same thing, except you're doing this over the y direction. And then for z center of mass, well, you just put in the correct variables, okay? And you do have to make this some function of x. Somehow you have to break it up into little bits of mass in the x direction. You have to break, if you're going to integrate over y, then you need to break this up into little bits of mass in the y direction. If you're going to integrate over z, you break this up into little bits of mass in the z direction, and so forth. Okay? If rho, which I haven't told you what rho is. Okay. So for objects that have a uniform density, so for uniform density objects, this board is shaking, I know, but maybe I can fix it. I don't know. All right, so if you have uniform density, then rho is equal to that total mass over the total volume, okay? And this gives you a way to integrate over the volume, which is sometimes easier. So in that case, you get xcm is equal to 1 over v times the integral of x d. Let me write it. That looks like velocity. dv, okay? And then y, same thing, y center mass is equal to 1 over v times the integral of y dv, and z, just for completeness, z center of mass is equal to 1 over v times the integral of z dv. Okay? Those are the equations. Let's do an example of this. Okay? And this example is, you know, it's pretty contrived. It's not difficult. This is very similar to what you've done in calculus, where you break things up into rings and shells and calculate volumes. And what we're going to do is we're going to do a 2D parabolic plate. So I'm going to have a little piece of a parabola that we'll imagine is a plate and calculate the center of mass along that y-axis for the parabola. Let me show you what it looks like. So here's the x and y axis, okay, and here's the parabola, all right? So it's an inverted parabola. You already know that this is second order, and I'll give it an equation. So this is y equals negative x squared plus 25. Okay. Really simple. All right. Hopefully, I mean, I drew it a little floppy, but what can you do? So obviously, I hope it's obvious that for the x center of mass, that's going to be at 0. It's symmetric about the x-axis. You've got the same amount of material in the same position on the left side as you do the right side, okay? So these center of mass problems, they do depend on where you make the x-axis. They don't depend, I mean, let me say that in a different way. The center of mass doesn't care where you make your coordinate system, okay, where you define your coordinate system. But for the calculation, it's important that you understand the relationship between whatever you're finding the center of mass for and where you define your coordinate system, okay? So I hope it's obvious that the center of mass in the x-axis, along the x-axis, is at 0. Okay, so I'm imagining this as a piece of plate, uniform density, and fairly thin. Doesn't have to be. I don't really care about the center of mass along the z direction. And I want to calculate the center of mass along the y direction. Okay? So from what I wrote down before, I'm going to change it just a little bit. So the mass is equal to, well, let me write this down. Y center of mass, I know I wrote it down a second ago, but Y center of mass is equal to 1 over big M times the integral of y dm. Okay? So what I'm going to do is I'm going to change these into variables that we can use for this 2D problem. And I'll show you how I'm going to do that. Okay. Let's say that this has some area which we can calculate. Okay. That has some area A. That's from here and around here. All right. M, this total mass, is equal to rho A. That's an area. This is an area density. Okay, so maybe I'll make that a little rho sub A. That has units of grams per square centimeter, grams per square meter, something like that. Okay. So that would be the total mass. Then dm is equal to rho A. This is a constant. This is some area density. Rho A dA. Okay? So that little bit of mass dm is some area density or density of the material times some little bit of area. Okay? So let's calculate the area of this object because we're going to need that. Then the integral becomes, let's see, the integral is going to become y center of mass is equal to 1 over A times the integral over y of dA. Okay? What happened to rho? Well, you had a rho A here and a rho A here, and they canceled. And since it's a uniform, if it weren't uniform density, that would not be the case. Okay? You would have to take into account that there's more mass over here than there is over here. All right? So, what I'm going to do is, first, we're going to need this. So I'm going to calculate that area. That's pretty easy. You know, everybody knows how to do that. Okay? So the area underneath the curve is the integral. What are these points? Well, those are the x-intercepts for the parabola, and that's -5, and that's 5, I think. Okay? That's the roots. Okay? So we have the integral from -5 to 5 of this. Negative x squared plus 25 dx. Okay? That's just for the area. I'm integrating. Now I can find the area integrating over y. That's harder. I'm not going to do that. All right. Do the integral. It's not difficult. Let me see what I came up with. Okay. This is equal to 500 over 3. Okay. Calculate it. 500 over 3. Now, we're going to have to I'm going to leave this up here. So we've already got big A. Big A is equal to 500 over 3. I'm going to write that. We'll squeeze it in over here. A is equal to 500 over 3. Okay? So now I've got to do this integral. The integral of y times dA. Okay? So I've got to break this up into little strips of area. And here's the way I'm going to break up those little strips. And let me get a different color. Hopefully this will show up. I don't know. So here's a little strip of area. Okay? This is this distance, because I want to integrate over y. That's dy, right? That little bit. And this width, I'll call this w. The width of this strip is w. Okay? So the area dA, let me get rid of this orange, it's annoying. So dA ends up equaling the width of that strip times dy. Okay, because I want to integrate over y. Because the integrand is y. Okay? So dA is the width of that strip times dy. So can we write an expression for the width of this strip? The answer is yes. Okay? The width of that strip is, in terms of y, you have y is equal to 25 minus x squared. So the width of that strip as a function of y, we need x as a function of y, because as you go up, x gets smaller and smaller and smaller, but we want that as a function of y. So all I'm going to do is solve this for x, okay? So you get x is equal to the square root of 25 minus y, okay? That's this distance x, all right? That's that little bit of distance that you have from the origin. So the total, and look, I realize this is plus or minus, but we're integrating, y is positive everywhere, and if I want to take into account that negative side just by symmetry, I just multiply this by 2. So w, what I call w, the width of the strip, that's equal to 2 times the square root of 25 minus y. Okay? Because that distance is 25 minus y, that's that positive distance, and I just double it. All right. So now we're ready to do the integral, because I have the integrand to 25 minus y, dA is w, that's w. dA is w dy, so do the integral. Okay. So where shall I write that? All right, I'm going to leave that up. So I need y, center of mass, is equal to 1 over a, we already calculated a, times the integral of w y dy. Okay? Because dA is w dy. So now, this plays the role of the mass, w dy plays the role of the mass, and that's the position. Okay? And as you're integrating, we're going to integrate from 0 up to the top. By the way, what is that top point? That's when x is equal to 0. So this point is 25. Okay? All right. So let's do this integral. I'll write it out. I'm going to go ahead and get rid of this and all of this. So y center of mass is equal to 1 over a times the integral from 0 to 25 of y times 2 square roots of 25 minus y. I don't know, gotta squeeze that in up there. So we have y, 2 times the square root of 25 minus y dy. Okay? Do the integral. And it's a little bit of work, not a whole lot. Make a substitution. So here's the substitution that you can use. Let y equal 25. Oh, I'm sorry. Let z. Most of you guys like to use u. So let u equal 25 minus y. Minus 5. Minus y. Okay. And du. Let u equal 25 minus y. So du equals minus dy. Make that substitution and you get an integral that is equal to, so y center of mass, and I'll go ahead and plug in a, which is 500 over 3. That gives you a 3 over 500 out front, and you get the 2 coming out front, and that gives you 3 over 250, because 1 over a is 3 over 500, and then the 2 came out, that made that 3 over 250. Then it's the integral from 0 to 25 of 25 u to the 1/2 minus u to the 3/2, and all of that times du. Okay? That's a u to the 1/2. Gosh, terrible u. Do the integral. That's pretty easy. And go through the calculation, and you get that y center of mass, after everything is all said and done, y center of mass is 10. So y center of mass, if this is 25, the halfway point's going to be 12.5, so it's about down here somewhere. That makes sense. Okay? You're looking for the point where you've got as much mass times position up here as mass times position down here, so the balance point ends up being somewhere around here. Okay? So that is the way that you would do a continuous object. Instead of point particles, you break it up into little bits of dm. Okay, and if you want to have I'll just generalize this. I guess I'll show you just a more general case. It doesn't matter where you place your coordinate system. If you want to place the coordinate system, in some strange place, say the object's out here and your coordinate 0 is here, that's fine. What you do is, let's say here's the x and y axis, and here is the object that you want to find the center of mass for. Well, you do what we talked about in the past. You break it up into little bits of mass, So here's delta M1, here's delta M2, here's delta M3, okay? So you break it up into little tiny bits of mass, and you have the position of all those masses. Call this R1. That's close enough. R2. Here's R3. Okay. And now I've only shown you 3, but obviously, hopefully it's obvious. I'm summing over the whole thing. Okay. So the center of mass, right, is equal to 1 over the total mass, is approximately, I'll just say approximately, equal to 1 over the total mass times the sum over I of R sub I, M sub I. Okay? Sorry, delta M sub I. Alright. So in this case, you know, this is not a very good approximation because I'm only breaking it up into 3. That's a really bad approximation. But anyway, oh, I should call this, I just said center of mass. This would be R center of mass, okay, as a vector. What do you do to find the center of mass? You make these deltas smaller, smaller, smaller. You break it up into more and more and more little pieces. You take the limit as delta goes to 0. That's equivalent to taking the limit as I goes to infinity. All right? You make it into a bunch of little point particles that are infinitely small. Okay? So R center of mass is equal to 1 over m times the integral over R dm. Okay? Where R is the position of all these little, you're integrating over the entire object. Okay, so that's how you would calculate it. Say you had a blob over here and you wanted to know the center of mass. Okay. So next time we will start talking about a little more about center of mass, and we'll start talking about linear momentum. Eventually we'll get to angular momentum, so that's objects that are spinning. We're not going to do that yet, that's later. But we're going to talk about this idea of if you throw an object, you have a projectile, how does it move in space relative to its center of mass? That is a very important concept in the sense of linear momentum. Linear momentum will give us the ability to do calculations with collisions. We'll look at objects smashing into one another and sticking together. We'll look at objects that come together and bounce off of one another like pool balls. We'll look at all different kinds of collisions. And the important thing about momentum is always conserved. It is one of those conserved quantities in nature, and any conserved quantity in nature is important for us in physics because you can do all kinds of models, okay, with conserved quantities that leads you into all kinds of nice physics. And momentum is one of those, linear momentum is one of those things that's always conserved. Angular momentum is conserved as well, but it's not quite as simple as linear momentum. And we'll also talk about impulse and how that relates to momentum. What we've been doing so far, we've been looking at objects, forces times distance, work, energy, all that stuff. With impulse, we'll look at forces multiplied by time. Okay? So that's it for right now. That's center of mass for point particles, center of mass for a continuous object or continuous objects. And probably the next video, what I'll do is we'll go over those homework problems that I assigned last night, I guess it was. And I hope you all are well, and I will talk to you later. Bye.